Buenos dias, eh? Buenos dias. That's a good morning to you. Oh. Hola. What is this? Multilingual day today? Bonjour, salut, ni hao. What else? Oh, sayonara is goodbye, but how do you say hello in Japan? Konnichiwa. What else is there? Ciao is goodbye in Italian. How do you say hello in Italian? Konnichiwa. Oh, salam. That's another one you could say. Is there any other way we can say hello? I don't know. I don't know. I do know one. In Thai, it's Sawatika. Ciao is hello and goodbye. Oh, I didn't know that. I know, like in Latin America, in some Latin and Central American countries, they say ciao as in goodbye. But I guess ciao in Italian is hello. Huh. Guten Tag. Is that German? Guten Tag. Guten Tag. That sounds German. Guten Tag. You ever see those? I forget what they're called. They're multilingual. Like they can speak more than like 7 languages or whatever. There's a name for them, and there's a YouTube videos of like 2 or 3 of them like having a conversation, and then like on the spot they're just changing languages up all the time. I think there should be just some universal language that everybody can speak, and then you can keep your own, language, English or Italian or whatever. But we should have like a world language. Just my thought. And then also, the way we're speaking English today. What's shikamu? Shikamu, is that is that hello, or is that the language you're trying to make? What is shikamu? Swedish. The Swedes, hey. Now I want to know more. But as my train of thought was this. I think that like the way we're speaking English today, in 100 years from now, it's going to be very different. So like if you look at the Victorian era of English, or even pre-Victorian era, they have a very distinct way of speaking English, which is different to ours. Even like British, the Britain version of English versus the American version of English, we can still like understand each other. There's a different accent to it, but you can still get the English. But like if you were talking about Shakespearean English versus English of today, like people wouldn't be able to understand. Well, I guess people who read Shakespeare and stuff wouldn't be able to understand what's going on unless like you actually delved into it. Just some food for thought. So all these videos I'm making are going to be rendered useless in 100 years because nobody's going to understand what I'm saying. There's going to be a whole different version of English. Oh, oh well. So today, before I begin, make sure you have your cup of water out. So, as promised, I'm going to be just reviewing some math today because we're going to need to know the math in order for us to do some of the later stuff. So the math I'm talking about is the math of vector calculus. And today, specifically, we're going to be talking about vector fields and divergence. So I know Zoe has learned this kind of stuff before, so it'll be a review for you. But Connie, I don't know if you've taken vector multivariable calculus. So this will be new to you. And then whoever else shows up, if they haven't taken multivariable calculus, this is probably going to be something new to them. But it's a very useful kind of math that we do. Maybe I should do this in Physics C in the beginning of the year when we review calculus for the non-calc people in the beginning. But I don't know. So we're going to be first talking about vector fields. So let's see. Okay, well, that's fine. This lesson is perfect for you then, because that's what we're going to be talking about. I'm assuming that you don't know. This is who the video is really intended for, and the people who just want a quick review. So I'm going to start from the beginning, give you a basic, fast version of vector fields. So what is a vector field? You've seen vector fields before. Maybe I just don't call them vector fields, but electric field is a type of vector field. The magnetic field is a type of electric field, is a type of vector field. Gravity is a type of vector field. What else? Water flowing down a river can be thought of a vector field. Is there any other type of vector fields I'm thinking of off the top of my head? No, I think that's it. Oh, wind. Wind can be considered a vector field as well. So what is a vector field? You know that let's look at a two-dimensional vector field here. So just in the XY plane here. So if we had a positive charge here, you know that it's going to have electric field lines all around. But they don't just stop right here. They're all over this plane. And you also know that the further you go, let's say you're right here now at this point, the magnitude is going to be less than the magnitude of the electric field there. And if you go even further down, then the magnitude there is going to be even smaller than there. And then over here, it's going to be even less and less and less. So we could map out the entire thing, and then we would get a vector field. Now, the way we're going to draw out our vector fields is we're not going to make the size of our arrows bigger or smaller. We're going to keep them the same. So in our vector fields, we're just drawing the direction of the vector field. And if you wanted to know how big it was, one way you could do that is use different colors. So let's say I wanted to represent a very large vector field being black. And then if I kept going down somewhere right here, I would draw the same size vector field, or the vector. So it's the same size as this one, except I'm using a different color. And that color will represent the size, like a hand wavy version of the size of the vector field. And the reason why we want to draw them the same size instead of this one really big and this one really small is because if you put arrows that are big and small all over this map right here, it's going to get confusing. It all mashes up together. So instead of doing that, we just keep the arrows the same size, and we can change the color if we wanted to, and that'll tell us an idea of what the vectors are going to look like. Now, if we were talking about a river flowing down, let's say downstream or something, we could, this is our river right here. And then the water doesn't just flow straight. Maybe there'll be some of the water going this way, some of the water goes that way. There might be a loop right here. What is that called? A vortex? Some of the water might flow that way, and then maybe some over here, and then all over here. So water isn't something that's going to be perfectly straight. It's going to be moving all different directions here. And these vector field lines tell us, oh, well, if we're right here, then the water is going to move that way. If we're right here at this point, the water will move down that way. This is a vector field of velocity, by the way. So they're very, very useful. Where are vector fields used? They're used all over the place, from like trying to map out the magnetic field of the Earth to finding weather patterns. So like when wind starts to flow, you draw a mathematical representation of the wind using vector fields. Okay, so that's the gist of what vector fields are. So how do we make a vector field? That's the first question. How do we make a vector field? The first thing is we need a vector. And I'm going to do a two-dimensional vector here. So this is how we draw out vector fields. Let's say my vector v, we could call that velocity, whatever, I don't care, is a vector in the x and y. Okay? And so there's going to be an x component and a y component. And in the x component, you can have x and y, which is weird. We don't really do that in math, but we don't do that in basic math, but you can. So in the I hat direction, I'm going to have a function x squared times y, and we'll call that in the I hat direction. And then we're going to add to it a different vector, 2 times x in the j hat. And it's weird to see that, because what we're saying is that in the up and down motion, it's going to depend on the x. So how much a vector is changing in the up and down will depend on x, not y. So here in the I direction, left and right, it's going to depend on x and y, but in the y direction, or in the j hat direction, it's only going to depend on x. So there's my vector field. Now what you should notice from here is that there's two functions. There's this function right here, and then there's this function right here. We can call this function, we'll denote that as p, as a function of x, y. And then this was different, this is different than that, so we have to use a different function. We'll call it q as a function of x, y. And so I'm going to rewrite this vector in a more general form. The general form for any vector in 2 dimensions, we could write like this. X, y is given by, I guess this is a matrix, p as a function of x, y. And then underneath there would be q as a function of x, y. And so what I've written right here that we're used to seeing, if you haven't done any sort of multivariable calculus or anything, this is the way we're used to seeing it in physics C, at least. What I'm saying is we can now rewrite it like this. So when you see p as a function of x, y, what you should think of is, oh, that's the function in the I hat direction. When you see q as a function of x, y, you say, oh, that's the j hat function, okay? Or the j hat direction. Now, something to note is that pxy doesn't have a direction. The I hat is the direction. So p as a function of xy, when I write this, and then q as a function of xy, is the size, right? So this is the size part. This is the direction part right there. So here, up and down, like top and bottom represent the direction. And then this actually just represents a number. So what we can say, because there's no direction associated with p and q, it's this part that's the direction. We can say that p as a function of xy and q as a function of xy are scalars. Scalars don't have size. Remember, they're just they don't have direction. They just have size. So it's the scalar part multiplied by the direction. So this is the function I have, and I want you to draw a vector field that goes with it. Now, how do you do that? Well, you might not see it like that. So let's just write it the other way really quickly, and then we'll work it out. I'm going to write it in this form, x, y, and that's equal to x squared y, and this one's going to be 2x. Okay, so another way of saying this, when you read something like this, you could think of this as the input and this as the output. That's, I guess, what engineers would say. So this is the input, and then you get an output value. So let's say my first input value is going to be 0, 0. Then my output value would be 0, 0. Okay, that's not bad. And then we could do 1, 0. If we do 1, 0, well, x is 1. So we plug 1 into here. 1 squared times 0 is 0. And then you plug in 1 into here. Because x is equal to 1, you end up with 2. And we could do the same thing. Let's just do one more. Let's do 0, 1. So if that's my input, my output would be 0, 0, I believe. Yeah, because they both have x in them. So we get 0, 0. And then I'll just put one more in. Why not? Let's do -1, 0. So if we do -1, 0, we will get 0, 0, and then -1 times 2 is -2. Okay, so you've got your x and y coordinates here, and I wrote this wrong. It should have been 0, 0, like up and down. Doesn't matter. It does matter. So we can plot this now. You could think of these values as x and y, and then this is your vector that comes out of it. So when you're at 0, 0, at this point right here, when you're at 0, 0, the vector is going to be 0, 0 big. Next one, let's go to point 1, 0. So we're going to go 1 this way and then nothing from there. And then at 1, 0, at 1, 0, your vector is going to be 0 in the x, but it's going to go up 2. So it's not going to move anywhere along the y direction, but it is going to go up 2. So 1, 2, something like that. And that's what the vector at that point would look like. The next point is 0, 1. So at 0, 1, that's right here, there is no vector, okay? And because it's a 0, 0. And then finally, -1, 0. So we go back 1, and we don't go up or down. And then at that point, we're not moving in the x, but we are moving down 2. So we'll go down 2, 1, 2. And you can do this for all the values here. Now, you don't want to do that for all the values, right? Because what is it? It would take forever to do, like put all these in. But that's okay. That's why you have computers for. So computers, you can put this function in, and it'll plot the vector fields for you, which is really, really nice. So if you got a program like Mathematica or MATLAB or Maple, I think Maple does it too, you'll be able to plot these things. Okay, and if we did, I just want to do one more just to bring home the point here. Let's say we did -2, 1. So if I had the velocity 2, 0, 2, 0 would give me 0, and then 2 times 2 is 4. So at 2, x equals 2, we are going to go, so 2, 0, that's here, this point right there. Our vector is going to be 0 in the x, but it's going to be twice as big. And then you could plot over here, and you can see it being twice as big. Now, you can sort of see the problem here, as I was mentioning before. If I were to find a point right here, let's say if I wanted to know what the point right here would be, this would be 2, 1. If I plug in 2, 1, and I make this out, you can see that this vector is going to overlap this vector. And we don't want that. We don't want any overlapping. So what we do is we don't make the vector this big. We just put the direction of what it is and then make them all the same size. That's the whole idea. And you will get your vector fields that way. Okay? So that is how you make vector fields. Now, let's talk about, hopefully you have an understanding of vector fields, how to draw them. Now we're going to be talking about applications. And the first thing is divergence. So let's talk about the divergence. Divergence. Okay. So divergence is I hate words, you know. They should just be simple stuff, but whatever. We're going to use big fancy words here. We're going to use divergence. And so what is the divergence? So let me give you an intuitive sense of what divergence is, and think about where you've seen it in physics. So the intuitive sense is like this. It's really hot in my room right now, so after this is over, I'm going to take a nice long bath, even though I've already taken a shower. And in my bath, I've got a tub here that goes like this. So there's my tub. There's me inside. My bath is really huge, by the way. And so what we have is a faucet here that's going to allow water in. But then I didn't close the drain, and my drain is on this side right here. Okay? So my faucet and my drain are in opposite directions. And for this example, I'm using it. I know that faucets and drains are usually on the same side, but this is my house and this is my fantasy. This is how I do it, okay? So we got the water coming in this way, but I didn't close the drain fully. So what's going to happen is some of the water, maybe not as much going in, is going to go out. It's going to go through the drainage, okay? So you got water coming in, you got water leaving. Hopefully that you can visualize that. Now let's take a look at this from the top view right here. So from top down, this is what I would see. I would see some of the water. Let's use blue because we're talking about water here. Over on this side, what I would see is the water hitting a point right here and then spreading out. And then over here, at this point right here, we'll draw a little circle there. From the top of my tub, what I would see is the water going into the drain, no matter what direction you're going. Okay? And then finally, in between, we would have water that's moving from the left to the right. Hopefully you agree with that. So there are names for what's happening here. Well, what's amazing is we call this a sink right here, and that's actually what the name of this is. When the field lines are all going, like converging to a single point, as is here, we call that a sink. Over here, this is where our water is coming from, the faucet. This is our faucet right here. There's a name for that. It's called the source. So you have a source and you have a sink. And then over here, you've got the water flowing in that direction right there. Okay? And so what is divergence? We're going to break this diagram into 3 different parts. I'm going to erase this. We're going to look at it from here. We're going to look at it from between. And we're going to look at it after. So we're going to look at it from here first, then here, and then from here, part 3. Okay? So there's 3 different things going on here with our vector field. You can sort of think of this as vector fields here. Of course, there's going to be a little bit of reflection here. It's going to bounce back that way, but we're just looking at it from the source's point of view. So from right here, and then from right there. Those are the 3 parts. And what we want to know is what the divergence is going to be. So we write it like this. There's another notation, and I'll write it later, though. So the divergence of V is going to be as a function of xy. So this is my vector as a function of xy over here, is going to be greater than 0 at part A, point 1. So looking at point 1, at 1, which is right here, we would say that the divergence is greater than this. And why is that? Why is that? This is how I imagine divergence. I would say the field lines that are going in at a given point are going to be less than the field lines that are going out. Okay? So the incoming field lines in here are going to be less than the field lines going out. Here's how I'd look at it. Let's look at this specific point right there. So I'm going to put a little box. I'm going to put that little point right there. At that point, there is no vectors. There's no lines there. Okay, this is where you really need to pay attention here if you want to understand divergence. So we're looking at this specific point, and I've boxed it in. At the point, there is no field lines, but afterwards, there are field lines going in all different directions. When you have a situation like this, there are no field lines, and then right afterwards, there are field lines. What we would say is that the divergence is bigger than 0, okay? Another way to look at divergence being, so how am I going to write this? The incoming field lines are less than the outgoing field lines. Okay, so the amount of field lines going into this box versus out of the box is going to be different. So in here, at this very specific point, there's no field lines, and then going outwards, there would be. Now, another way we could draw this, another way we can represent this is like this. Imagine you had all these field lines, and we were looking at a specific point. We would box that point in, and what we would do, let's look at in terms of the x direction. If the number of field lines, or the size of the field line, the size of the vector, I guess is what I should say. What color should I use? Blue. Let's say that the size of the vector going in, and then compared to the size of the vector going out from this space right here, if the size going out is bigger than the size going in, your divergence is greater than 0. Now, this isn't any math here. I'm just giving you an intuitive sense of what's going on here. And it doesn't matter which direction you go either. So we could have had something like this. This would also create a positive divergence. Let's say we were looking at a point right here. We boxed it in. And then we saw the vector field lines going the other way. So if you had small vector field lines going out, and then larger ones going in is small, and then coming out, the field lines are bigger, there is positive divergence here. And this is along the x, but you can do the same thing in the y direction. You can also do it at an angle. So let's say we had a point right here in space, and the field lines were going in at some diagonal like this. They're going in this way, but they're coming out much larger. So let's say this is x equals 5, and this was x equals 6, and this was x equals 4 right here. At x equals 4, you can see that these vector lines are much bigger than these vector lines right here. And it doesn't matter, I'll say it one more time, whether you're going left or right. It depends on the size of the arrows that are going in and out. So here the arrows were going this way. Here the arrows were going that way. So this would be the input. Over here, it would be the input. This side, because the arrows are pointing outwards, would be the output. So when the output is bigger than the input, when the output is bigger than the input, you have positive divergence. And that's what's happening here. There is no input here. There's only output. This is an extreme example, but there's only outputs going on here. Nothing is going in. So the output is definitely bigger than the input because nothing is going in. divergence is greater than 0. And where have you seen something like this? Positive charges. Positive charges, positive divergence. That's kind of the idea there. So there's that. Now, at section 2 of our water diagram here, the divergence is going to equal 0. So if we look here in our faucet, in our tub, we can see that the value of the vectors going in and out are going to be exactly the same. So over here, if we drew a box, let's say this is my point right here, and I put a box around it, what I would see is that the amount of water that's going in, the size of these arrows, and the size of the arrows coming out are identical. So if the input is equal to the output, you get no divergence. All right. And then finally, at section 3, they're all going in. Nothing is coming out. So if I were to look at that specific point at part 3 right there, and I boxed it, what I would see is only field lines going in. Okay? So what are you comparing these field lines that are going into? Nothing going out. So the output here is 0. So you're comparing this arrow right here that's going in to something that's 0. So the input arrow is bigger than the output arrow. And that's when you get negative divergence. So if there's more field lines going in than out, then you get negative divergence. And where have you seen negative before? Negative charges, field lines go in. But that's for physics. This is math right here. We'll stick to our math here. So this is the extreme case where all the field lines are going in, but nothing going out. You can also have negative divergence if you have a situation like this, where let's say there's a bunch of field lines, and the arrows that are going in, which way do we want to draw them? Let's draw them in the y direction. So let's say the arrows going in are this big, but the arrows coming out are that big. So the input arrows are bigger than the magnitude of the input arrows are bigger than the output. And let's say there's nothing happening in the x direction here. This you would see as negative divergence. The reason why I'm showing you this is because I want you to have an intuitive sense of what divergence is going to be without even doing the math. If you've got vector fields like this, and you could just look at them without doing any sort of derivatives or anything like that, you could tell right away, oh, well, that's going to be positive divergence, that's going to be 0 divergence, that's going to be negative divergence. Or if I tell you, oh, this is going to have negative divergence, in your head, you should be like, what does negative divergence mean? Oh, yeah, that's when the arrows going in are bigger than the arrows going out. That's what I should expect to see there. So that's the intuitive way of thinking about it. Okay. So just a little bit more. Let's put some more math into it because, you know, everybody loves math. So we're talking about divergence, and what we'll do is we're going to let the vector fields only go in the x direction here, just to make our vectors a little bit easier to solve. So we're going to say let v as a function of xy equal p as a function of xy in the I hat plus 0 in the j hat. So when you see this, there is no up and, like the up and down vector, there is no up and down vector. I mean, there's going to be an up and down vector, but it's only going to depend on the x. So what does, when you see something like this, or I guess I should write it like this as well. If you see let v as a function of xy equal p xy and then 0 right here, when you see that, what you should think about is there's nothing happening in the y. There's no y vector here. So when I plot this, this is my graph right here, what I would see is whatever this function is, it could be like an arrow. Maybe there's nothing here, but then you get a bigger arrow. You got an arrow here. You got an arrow here. And then if you go up, y equals 1, it's going to be the same value arrow. And then maybe there's an arrow going backwards at this point right here. I don't know. It depends on what the function is. And it's going to be the same thing over here. It's going to go like that, 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 and then over here, that, that. So what this is implying is that as you go up in the y direction or down in the y direction, nothing's going to happen. It's going to stay the same because it's only dependent on the x. Okay? Whoa. Cut myself again. So that's what this is saying when you see something like this. Just making sure we're all on the same page. Okay. So the reason why I'm doing that is because I want to look at divergence only along the x direction, and we can do one in the y direction as well. So let's say I have that, and what would positive divergence look like? What would positive divergence look like? So in the case of divergence, I already said this, but we're just going to put it in a different form here. Divergence of v as a function of xy. If we want divergence equaling xy, equaling greater than 0, then what kind of scenarios would you see? Well, you could see one scenario where you have point P right here, and that's the point that we're interested in. It's somewhere in space. It's somewhere in the two-dimensional space right here, and we're going to box it in. And we're going to look at only the x vectors because there's no y vectors here. So when would you get divergence greater than 0? Well, there could be one situation where there's no vector on P, but immediately right after it, you have a vector that's going in this direction here. What color should I use? Blue. And then maybe over here, we're going to go this way. Like that. So here, everything is going outwards. Nothing is going in to the point P right there. And so we have positive divergence here. What else can we say? So the function P as a function of x, what color? Over here, let's say this is the origin. So this is P equaling 0. And then this is a xy coordinate plane, by the way. So this is P when 0. This is going to be P greater than 0 because you're moving forward. This is going to be P less than 0 going this way. But it doesn't matter what P is if it's greater than, equal to, or less than 0. We don't care about that. What we care about is the divergence. And the divergence is saying that at point P, there is no input, but there is output. At point P, there is no input, there is output. Now, if I was to look at a new point, let's say point Q over here, this is point, no, I won't use Q, let's use point R. And I was to make a little box right here, I would say the divergence for R is 0 because the vector going in and out are the same. But at point P, this is what it looks like. Let's look at another situation. Let's say that P is not equal to 0, okay? Let's look at the situation where P is not equal to 0. So let's say here's my point P right here. I shouldn't use point P because I'm confusing you with what P and P is. So let's look at this point right here. And at this point, there's going to be a P value, and the P value is going to be this big. And then immediately afterwards, there's going to be another P value that's this big. And then before that, there's going to be a P value that is maybe even smaller, maybe this big. So over here, the P value is, I guess, how am I going to say this? This would be, because they're all pointing in this direction, P is positive. So P is greater than, much greater than 0. Over here, this blue line represents P being greater than, much greater than 0. And over here, it's going to be P only greater than 0. So by writing it this way, what I'm saying is that the arrow sizes are different. And so if we look at this specific point right here, you can see that the P value that's going in is not as big as the P value going out. And therefore, you have positive divergence. And then this is for p greater than 0. Let's quickly just do p less than 0, just so we, for completeness. If I have a specific point like this, and now the vector field lines are pointing in the opposite direction. So let's say this one is like that, and then this one's much bigger, and then this one's even bigger. Here, p is going to be p is going to be less than 0. Over here, p is going to be much less than 0. Or I think I wrote that backwards. So p is going to be much, much, much less than 0. P is going to be much, much less than 0. And p is going to be less than 0. So when the arrows were pointing that way, we said p was greater than 0. When the arrows are pointing that way, we say p is less than 0. And this arrow is much bigger than that arrow. And you can just box the point that you're interested in. And the field line going in is much less than the field line going out. So once again, you have positive divergence. Okay? So the direction of the arrows don't matter. It's what's going in and what's coming out that matters with divergence. Okay? And another way we could write this, because we're only interested in p, is like this. dp over dx is going to be greater than 0. So when you see dp over dx, what that's saying is that the divergence along the x direction is bigger than 0. Okay? So if you see this somewhere, you have to interpret it as long as you're looking at only what's going on left and right, think about what's going in and what's going out. If what's going in is less than what's going out, that's what's happening. All right? Am I confusing you, or are you actually getting this? Somebody say something. Somebody. All right, good. So let's look at the y component, and we're going to do the same thing. So here we're going to say it's 0 in the I hat plus qxy in the j hat. Hey, Sean. So we could write that as v as a function of x, y equals 0 and then q, x, y. So that and that are identical statements here. And let's do the situation where now we're looking at in the y direction. So it's going to be dq over dy. And what are we going to do here? We're going to say dq over dy is going to be less than 0. Let's look at the situation where dq over dy is less than 0. So what we're saying here is the divergence along the y direction is less than 0. So the input has to be bigger than the output. Here's my little point right here. We put a little box around it. And if you want this statement, then what you should see is the vector field lines that are going in are much bigger or bigger than the output going. And so here, this would be q less than 0. And this would be q just less than 0. So both of them, all this q being less than 0 just means that q is pointing down. So this is down, but this one is going to has a larger value than this one. So the input bigger than the output, that's true right there. The other one could be like this. We got a point here. And then we could be going up. Okay, it's the same idea. So going up now, and then going up a little bit. So the input bigger than the output. And in this situation, q is much bigger than 0, and here Q is bigger than 0. So the input bigger than the output, and that's fine. And lastly, you can have a value inside of the arrow as well. That's fine too. At that point, you can have something. So if we did this, and let's say that inside the box, at this point right here, you had a value Q going up, and then the value right here is even bigger, and then the value here is even less. This is negative divergence along the y direction. All right. And if you wanted positive divergence, then you just, did I say that wrong? I said that one wrong, didn't I? Let me rewrite that. So the input has to be bigger than the output. Okay, so that's what I wanted to draw. So here you would get negative divergence. But if I had the other picture, then the divergence would be the opposite way around. Okay. I hope we're good. We're good with that. Let's keep going. And I got to find my notes here. Here we go. Let's put it all together. We have divergence in the x direction, divergence in the y direction. What does divergence look like in the x and y direction? So here we're going to have v as a function of x, y. And I'm going to write it in this notation now because hopefully you understand it. P as a function of x, y, q as a function of x, y. So there's our vector here. And the way we're going to write down divergence is like this. The divergence of v is given by the derivative of each part, the partial derivative. So it would be dp over dx plus dq over dy. And it's the partial derivative that we're interested in. So if this term, let's say this is what our divergence equation is. Let's imagine now what would happen. Like, what would things look like if we had this scenario? I don't know. Let's do one. Let's say that the divergence along the x direction is greater than 0, and the divergence along the y direction is going to be less than 0. Or let's do greater than on both cases. Make our lives a little bit easier first. So both of these are greater than. What does that imply? Let's look at a point right here and see what kind of situations would allow us to do that. Let's just go positive, and then we'll do other ones as well. So the input has to be less than the output. So in the x direction, we're going to go like this. There's going to be an arrow going in that way, and then there's going to be an arrow coming out that's going to be bigger. So the input is less than the output. That takes care of that. How about the divergence in the y direction? Well, again, the input has to be less than the output, like that. And so when you see a situation where it's this and this together, one example that you can get is you just combine the two vectors together. So these two combine going in this direction right here. What color? We'll use brown. We can use head to tail right here. And this vector right here represents these two inputs going that way. So we don't need this anymore. And then this and this, when you use head to tail, so you bring this one, you swipe it over, and it'll be up here. And you can draw a vector going that way. And there you go. So when you have both positive this and this, here's one example of what it would look like. Here's another example, because I remember I said that the direction doesn't really matter as long as the input is less than the output. So we could have done something like this. I'll just do it really quickly. And this is just trivial, but it's good to know. let's say that the x was actually going in the other way. So here, this was the input, and this was the output. And the y remained the same as we did before, the input and then the output, like that. Well, when we combine our two vectors, we'll still get the same kind of idea. So if I combine this and this together to get my resultant vector for the input, it's going to look something like that. And we can get rid of this and this. And when I combine these two together, I'll get a resultant vector that looks like this. And once again, the thing that's going in and the thing that's coming out are different. So here you have positive divergence in both situations. All right. So the input here and then the output there. Now where it gets interesting is when these two things kind of get screwy. Then you have to actually like think about what's going on. Let's say that this is less than 0. So if it's less than 0, what's it going to look like? We can plot it. And let's do y going down this way. So if this is less, that means the input has to be bigger than the vector coming out. And for here, it remains the same. Let's go along this direction here. So you have the input going this way, and then the output would be much larger. Okay? And so from here, you're going to get something different here. So what's going on here? You have this and this. They're going to give you something that's going in this direction, I guess. And then these two together are going to give you something else. Okay? So you combine these two vectors and you combine these two vectors in some way or shape. And it's going to really depend on which one is bigger. So if this one is much, much bigger than this one, then the overall divergence is going to be positive. Or actually, it doesn't have to be much bigger than. If this is bigger, or let's say this is positive and this is negative, if this is more positive than this is negative, then the divergence is going to be positive overall. Because what the divergence is a scalar quantity. So this is going to give you a number. This is going to give you a number. And if the positive number is bigger than the negative number, you get a positive number overall. That's the whole idea. So let's say this value was bigger than this value here, then you would end up with a positive divergence. But if the y part is more negative than this is positive, then the divergence would be negative. So overall, you would say that the thing that's going in is greater than the thing that's going out. Okay? So that is how we look at divergence. And there's just one more thing I want to say. About it, and it's this. The actual notation for divergence. Divergence, I've been writing it like this. Some of you are probably cringing about that. X, Y. The way we really write it is this. We write the opposite delta. It's like the flip of delta sign that we normally use in physics, which is called the del operator, multiplied by, it's a dot product. So it's going to be this times this. Now, this del operator is actually a vector. So when you dot a vector with a vector like A dot B, you get a scalar quantity C. That doesn't have a vector there. And it's going to be the same thing over here. When you take a vector and you dot it with a vector V, which is this, you will get a scalar quantity. And the way we can write this, if we're going to use our notations here, this is really just derivatives in x and y, or z. So we'd write as dx, or d over dx in the I, and d over dy in the j, and you're multiplying that by velocity, and we said, or vector v here, and vector v is made up of two parts, which is p as a function of xy and q as a function of xy. So when you take the dot of these two, what you get is our equation that we just wrote down before. It would be this times that, which is dp over dx plus this and this, which is going to be dq over dy. And that is equal to the divergence of any vector. And you can expand this to include 3 dimensions. So if we had the gradient of the del operator multiplied by v as a function of x, y, z, then that would equal dp over dx plus dq over dy plus dr pqr over dz. And then you just add to it that way. So that is as much as I wanted to say about that, and that's as far as I'll go with the math here. Tomorrow we'll continue back with the physics part and how it applies to this divergence that we're looking at. And I will also, well, actually I lied. We are going to be talking a little bit more math. We're going to be actually proving the divergence theorem. So that'll be tomorrow. But what I wanted you to get from today's lesson is what divergence is. So when you see divergence, it's the derivative of a 2-dimensional thing. And what you're really looking at is what's going in and what's going out, okay? That's all divergence really means, is the stuff that's going in, the vector field lines that are going in versus the field lines that are going out. Or at least that's how I interpret it as. Maybe somebody interprets it differently. So 2-dimensional derivatives here. We got partial derivatives. Here's what's really cool. Should I? I'll mention it. There's another thing you can do here. If you square the del operator, so if you take the second derivative of this, you will get something called the Laplacian. And we can talk about Laplace later. Laplace is super important for like more advanced kinds of physics stuff, like the heat equation and what other stuff. I'm not going to say it right now. But there it is. That was today's lesson. Hopefully you got a little bit of good review from that. Hopefully your mind is working a little bit. It's not dulling out. And that's all I got to say. I will see you tomorrow. See ya. Adios. Or at 5, whichever comes. Adios, adios, adios.